Let me see. So, okay. So can you see my screen? So sometimes I'm just confused. Which screen do you see? Do you see the screen in the?
No, it's perfect. Yeah, we see it.
It's okay. Okay.
Yes.
Okay. It's really a great pleasure to be here and to meet a lot of old friends that we haven't seen each other for a long time. And today I'd like to just share some of our research progress on the surface electromagnetics. And I'm from Tsinghua University. And so we are all familiar with electromagnetics, but here I put surface before that, because if we look at the surface in the nature, so we see the moons, we see the notice leaves, we see the surface of a silicon substrate in the nanoscale. They are really very fascinating, and they have very interesting physical and chemical features. And if we look at the surface, we see a lot of interesting remarks, and I would like to call two of them here. The first one is by Democritus, 400 years BC, and he said the essence of a thing is hidden in its interior, while the sensitive qualities are caused by the surface. So by touch, by see the surface, we can understand what is inside, but sometimes this can be very misleading. And another statement is by Wolfgang Pauli, and he said, God made solid, but surface was the work of the devil. It's really confusing, well, yet it is very interesting. So that's why we are interested in the surface. And of course, we see a lot of distinguished achievements on the surface. Like, for example, if we look at 1921, Einstein, he won the Nobel Prize because of the photoelectric effect. So that's basically the light illuminate on conductive surface. And then later on, if we look at the transistor, it's also some surface effect. So if we have some kind of semiconductor with different doping, when they touch each other, so this kind of surface effect, so they will have this transistor. And then more recently, if we look at another example in 1986, Pinnick and Rojo, they won the Nobel Prize because of their contribution on the scanning tunneling microscope. With that, people can see and can manipulate the atom layer of a surface. And more recently, we are more familiar is because of the two-dimensional graphene. It's also a two-dimensional surface structures. So we see there's a lot of achievement with the surface. And if you look nowadays, we see the surface science in different disciplines, like the surface mechanics, the surface chemistry. So basically with the surface effect, so one can expedite the reaction of a chemical process. And of course, the surface physics, the two-dimensional materials, and so on. Our interest here is of course, the electromagnetics together with the surface. So that's what I'm going to share with you today. So with that, a brief introduction. So here's what I would like to discuss today. The first part will be the development overview of the surface electromagnetics. And then I will show just one representative example of the surface electromagnetics, very interesting. And then following that, we'll show some devices and a system based on the surface electromagnetics. And then finally, some prospectors. So when we talk about electromagnetic surface, the first one we are thinking about is the classical electromagnetic surface. For example, interface between the free space and the conductor, or the interface between two different materials. So this type of surface we call it uniform surface, because along the tangential direction of the surface, there's partial derivative equal to 0. So there's no variance in the tangential direction along the surface. And then for this one, the reflection and refraction, they follow Snell's laws. And of course, we have some interesting phenomena like the total reflection angle or zero reflection angle. So that's the Brewster angle. So this is a classical uniform surface. Okay. And then in the middle of the last century, around 1950, 1960, and 1970, people start to look at the periodic surface that's known as frequency selective surface. like in my personal opinion, so it is really a giant step. It's just like the circuit. It moved from the DC to AC, from the direct current to alternating current, from the uniform surface to the periodic surface, but now it is periodic in space. And this surface can operate as a space filter. So basically, if the frequency is within the passband, the electromagnetic wave can pass through, otherwise it will be reflected. So here we are looking at the amplitude response of the surface. And then there's a lot of applications, and one of them is to be used as a sub-reflector for parabolic reflector. So basically for the S-band, it is transparent, so it goes through. And for the XKU and KA band, it serves as the sub-reflector, it will be total reflection. So this is a FSS. So we are looking at the amplitude feature. And when I was a PhD student around year 2000, we are interested to see the phase features. So that we are looking at the artificial magnetic conductor. Using this periodic structure, if you look at the phase response with respect to frequency, we notice at a certain frequency, we get a 0-degree reflection phase, those resembling a perfect magnetic conductor, which does not exist in nature. So this we call artificial magnetic conductor, and we are looking at the phase feature. And more recently, we see some new progresses. For example, this is the work in 2011 in Science Journal. It's a talk about generalized modes of reflection and reflection using the phase discontinuities. So by using the nanorod assembled like this, the reflection and refraction angle can be manipulated as required. But similar thing also happen in microwave. For example, we can also control the rotation of each element or by varying the size of each element. So we can also do the similar things. And this structure, I would like to call it quasi-periodic. So basically every element is located on periodic lattice, but each element is different. So if we put all of them into one slide, just resembling the circuit and signal that we studied, we start with the DC signal, DC circuit, and then AC signal, and then later on the modulated signal. But these are in terms of the time domain. And surface, we are dealing with the space domain. And started with uniform surface. For example, we use that to design parabolic shaped reflector. And then with the periodic surface, just like AC signal, and we can design the frequency selective surface, we can design the EBG, artificial magnetic conductor. And then with space modulation, instead of the time modulation, so we can design the reflectarray antennas, transmitarray antennas, and so on. And more recently, so we are trying to combine the time modulation and space modulation together. So basically each element will be time controlled, and then by a spatial distribution, so we will be able to realize some new design of phased array antenna, for example. So this is the development. And then nowadays, if you look at the, so for example, IEEE transaction on antenna propagation and other journals, we see many different electromagnetic surface. When we talk about the magnitude response, so we have the frequency selective surface, in the optical region, the gratings, absorbers, and so on. So if you look at the phase response, so we have the artificial magnetic conductor, the phase shifting surface, the holographic surface, and of course, if you look at the polarization, we have the polarization converter or polarization grid. And moreover, instead of plane wave, we deal with surface wave as well. We have the so-called soft and hard surfaces by Professor Kilda, the high impedance surface, EBG surface, and so on. So more recently, we have a lot of general terminologies like Huygens surface, metasurface, and so on. And now if we add active functions, so we have the reconfigurable surface, programmable surface, or with some amplifier or oscillator, we have grid arrays. So there's a lot of interesting happening right here. And with that, I would like to see, so this is really a lot of things happening and in surface electromagnetics. So we see all these surface, but where does it originate from? Of course, from the Maxwell equations. So we look at those 4 equations and we see the behavior of the electric field and magnetic field vary with respect to the time and with respect to the space. So when we look at different phenomena, usually we classify them into different categories. One way we classify this electromagnetic phenomena is based on their time behavior, basically how fast the wave oscillates. So we have from DC AC to the RF, microwave, millimeter wave, terahertz, and go all the way to the infrared, visible, UV light, X-ray, gamma ray. So all these classification, so it's based on the time behavior. So we said we talk about their variation with respect to time and space. So how about classify them according to the space features? So in general, if our structure or our scatterer or antenna, if their dimensions are comparable to the wavelengths, we have Lx, Ly, and Lz, all comparable to the wavelength. So we have to rely on Maxwell equation using the general electromagnetic theory to deal with that. So usually we are able to analyze them with this computational power, but usually the synthesis is really time consuming. On the other side, when we look at the circuit, all their devices, connecting wires, the R, L, and C, they are much, much smaller compared to the wavelengths. So in terms of the spatial feature, we would like to call them 0 dimension. Okay. And then as the frequency goes up and the wavelength becomes smaller, so we see now the line become transmission line. We have to consider the line length effect. So basically the length is comparable to wavelengths. So this is, we call it 1-dimensional transmission line theory. So by looking at this graph, we see we have 3-dimensional, 0-dimensional, 1-dimensional, and the 2-dimensional actually is a region that we need to deeply investigate. So then if we look at the surface with their horizontal dimensions, Lx and Ly, if they are comparable to wavelength, but their thickness are much smaller compared to the wavelengths. So this is surface electromagnetic. So we call it the 2-dimensional electromagnetic phenomena. That actually that's our interest is right now. So when we look at this surface electromagnetic research, the foundation, I think, can go back to the Huygens principle. So if we are able to manipulate the wavefront, so we can change the wave propagation after that. And that's from physical viewpoint. From the mathematical viewpoint, so when we solve Maxwell equation, so we usually solve Maxwell equation with certain boundary conditions. So based on the uniqueness theorem, if we know the boundary condition, and we can solve for unique solution of this one. So that's why we see many electromagnetic problems, they are called boundary value problem. So that's the importance of the boundary. And also we are also familiar with the surface equivalence theorem as shown on the right. So basically we have a original problem with E1, H1 as the radiation field. But say if we're only interested in the E1 and H1 outside the surface S, so we can have arbitrary E and H inside S as far as the boundary condition JS and MS are satisfied. We will have the same outside field as the original problem. So basically that tells us how we manipulate or how we use the surface feature. So we have a lot of application of using this surface theorem. One way to use that, or the traditional way we do that, is we know the field inside. So by simulation or by measurement, we find the equivalent surface on surface. And then from that, we find what is outside radiation. And then for the synthesis, we will do a little bit different. That means we know what is inside. And we know what outside field we expect to have. And from that, we are trying to design the surface. Okay, for example, the reflectarray design is such an example. And then in order to do this surface design, usually we have two things to discuss. The first thing is usually we have to digitize the surface. Traditional, we may have a continuous surface. But now we would like to discretize the surface based on the sampling principle. So the surface is discretized into small unit cells, usually less than half wavelengths. And then each unit cell will have individual control capability of the local electromagnetic wave. And then with a certain surface distribution, so we will have a global control of the wavefront. And then in particular, if we do the wave control of each unit cell, so usually it is required to have simultaneous magnitude, phase, and polarization control. And more advanced, consider the vector feature of the wave. So we may have anisotropic or even bi-anisotropic feature of the surface. It operates with the visible range for optic instant and invisible spectrum for surface wave. It has certain dispersion feature, the bandwidth feature, or even nonlinear property. Of course, if we add real-time control, we integrate circuit that will also enable more functionalities. So that's about surface. And before I close this first part, so I would like to bring some comparison. The first is a comparison between the transmission line filter and the EM surface filter. So the one on the left is a filter, and in this filter design, all the transverse dimension, for example, the width of this microstrip line or the height of this microstrip line, the height of substrate, they are smaller compared to wavelengths. But their longitudinal dimension, like this coupling line, their lengths are compared to wavelengths. The one on the right is a space filter. Their transverse dimension, x, y, are comparable to the wavelengths. And their longitudinal dimension, thickness, are much, much smaller compared to the wavelength. So this is really a very nice duality of each other. And we know the transmission line theory is the fundamental basis of all microwave circuit. So with that, we can think of the importance of the surface electromagnetics will never be overestimated. So that's one comparison. Another comparison very interesting is to compare the terahertz with the surface electromagnetics. We know terahertz, we know that for a long time, but it only become a hot topic recently. It's considered a new frontier of electromagnetic, but in the time domain. And we have the new IEEE transaction on terahertz in 2011. So that shows the fast development of terahertz research. And then surface electromagnetic research, of course, we all know that for a long time, but it only now become very active frontier, but this now it is in space domain. And also for our current research, we're trying to apply the surface electromagnetic for many terahertz antenna and system design. And it's really a very promising potential in both the science and engineering. Because in terahertz, usually the transmission line can be really lossy. So the surface will be a good alternative for terahertz system design. The last comparison is I would like to make is about the metamaterials versus metasurface. Okay, usually the metamaterials are 3D volumetric structures. Now we are talking about 2D surface. And on the left one for metamaterial, usually we use the equivalent constitutive parameters. And for surface, usually we rely on the boundary conditions. And then surface has a lot of advantage. For example, it is easy to fabricate, no profile, lightweight, no cost, and so on. And it is thus more preferred in engineering applications. And also we see a lot of people are more interested in the metasurface nowadays. Look, that's my first part. And next is representative examples in the surface electromagnetics. So let's just bring this a simple question. So if we have a surface, and then we have a wave normally illuminate on the surface and after surface, we would like the wave will be bent to an oblique direction. So we would like to design such a surface. So for the requirement, in terms of the geometry, so it is expect the surface thickness will be much smaller than the wavelength. So the h is much, much smaller than wavelength. So we consider it is a surface. Regarding the electromagnetic characteristics, the transmission magnitude we expect to be close to 1. So we have the total energy transmission. And then for the phase, we would like to have a full phase range of 360 degrees. For example, if we have the 0, 90, 180, 270, 360, and then the wave will be bented. So that's the 3 requirements: the thickness, the magnitude, and the phase range. So we start with the first design. We have a PC ground, and then on the PC ground, we have periodic slot cut on this ground. And then when the slot resonant, so we have full energy transmission. So as we can see here, so we have a total transmission at 12.5 gigahertz near 0 dB, and the thickness, because it's single layer, is close to 0. But if we look at the phase response within this 1 dB bandwidth, we look at the phase response. We go from 27 to -27. It only have 54 degrees. So now we think maybe if we introduce a wideband design, so we do another design, we increase the width from 0.1 millimeter to 0.5 millimeter. So we get this red curve. So we see the bandwidth is from 5.2% to 7.8%. But now if you look at the phase response, even though the bandwidth is wider, but the phase slope is smaller. So if you look at this point and this point, we get the phase range again from 27 to -27. We still have 54 degrees, much less than 360. So my student, they give out another design. Is that if the wideband does not help, how about multi-resonance? So he designed a double square loop. And if you look at response, so we have a magnitude 1 resonance, another resonance, and then this green one is the phase. But if you look at the 1 dB right here, we get the phase from here to here. It's again 54 degrees. So if you cut from here, you also have this within the ±27. So this is really interesting. So we stop at that point and we try to find out what is behind these 54 degrees. So we start to do some analytical derivation. So we choose a general surface. We still assume them to be very, very thin. We have incident, we have reflected, and we have transmitted. And then according to the field continuity, no matter if it's a conductor or it is dielectric, we always have the tangential E field to be continuous. With that, we have the 1 plus R equal to T. So this R and the T can be a complex number. Another condition we use is to use energy conservation. If the surface is lossless, so we should have R squared plus T squared equal to 1. And then we do some manipulation. For the complex value T, we have with magnitude smaller t and the phase phi right here. So R equal to T minus 1. We take into this equation here, and we do some manipulation, and finally we get, so the transmission magnitude equal to the cosine value of the transmission phase. In other words, that means the transmission coefficient cannot be arbitrary. Their magnitude and their phase are dependent on each other. So to further understand this equation, so we plot out the 1, T, and R as a vector in the polar diagram. So basically, this is vector 1, 1 plus R equal to T, the blue one. And R squared plus T squared equal to 1. So this is a right triangle. So basically, T right here equal to the 1 times the cosine of the phi. So that means this transmission coefficient T must always be on this dashed circle. And of course, R equal to T minus 1. R must be on this circle. So now if we just take the T circle out, so T must always be on this blue circle. So if it is on this blue circle, if it is above minus 1 dB, so we go from here to here. So that's plus minus 27 degrees. So that explains no matter what kind of circuit we have, if there's a if it's a general, very, very thin surface that satisfies these two conditions, we will have this 1 dB passband with a phase of 54 degrees. So with this analytical result ready, so we go back to see some geometries. We have the cross dipole, square loop, and also the complementary geometry cross slot. If we look at the magnitude and response, and the phase response, they look quite different. But when we plot them on this polar diagram, so this is the cross dipole from here, total transmission, and then go to the total reflection, and go on. And then square loop, the same, but it can cover more area or the more space on this loop. And then for the cross slot, it goes from the center right here, and it go out, and then from here, and here we get total transmission, and then keep on going. So although they look quite different, they are always on this analytical circle. We also look at this dual resonance. It's still the phenomenon. We go from 7 to 11, one resonance, go up to 14, and then go to 7.1 again, another resonance. It's only, it follows the same magnitude and phase relation, but it covers the full circle twice due to the dual resonance feature. So that we understand now the single layer will not help us to get the phase range. So with that, how to enhance the phase range? So we go to multi-layer design. And now we already have some experience. So we start with some analytical derivation. So for example, if we have the double layer, we have a full coverage of the bottom, but the top part is missing. And the triple layer, we have a wide coverage, but we still have a very small gap here. And then if we have quarter layer, so we have full layer, and then we can have full coverage above 1 dB. So the solid line is the analytical result, and the dotted line, these are the simulation result of a specific geometry. They match very well. But the only thing right now is we have good magnitude and we have a good phase. But the thickness, each layer is about quarter wavelength. Now we have about 3/4 of wavelength. So that's too thick. So now we revisit the procedure of the analytical derivation. We see we have a lot of assumptions here. For example, we assume each layer to be identical. But in practical design, we can use non-identical layers. So we use non-identical layer. We redo all this analytical derivation, and then we find 3 layers will be sufficient. But the 2 layer is still not enough. So we need 3 layers. And another assumption we made is usually we only rely on the wave coupling. So that's from layer to layer here. So we rely on the wave coupling. But if we have the wave coupling together with a direct current from one layer to another layer through vias, so we will break this assumption and we can break the conclusion we got out in the previous slide. Also, because we are dealing with a vector field, the derivation, right, just now we only deal with co-polarization. If we take cross-polarization into the consideration, we can also break the limit. And of course, in the previous discussion, we only talk about fundamental flocate mode. So that's when we deal with the scattering matrix, we deal with the scattering matrix of the fundamental mode. If we are able to include a higher order mode coupling, so we can also break the limit. So with that in mind, we go ahead and we have some new design. So this is the design. Between the 2 layers, we also have vertical vias to connect the top and the bottom layer together. So if we design them properly, we can get the result shown on the right. So, sorry. So without the vias, so we have the analytical result, and then we have these blue triangles. So that's a simulation. They agree with each other. And then when we add the vertical vias, so this is what we obtain. So we can cover the entire polar diagram with the magnitude close to 1 and the phase covering the 360 degrees. So that's the, when we add the vertical vias, we break the assumption and break the limit. Another way is if you have cross pole. For example, if we design a square loop with a defect, and if we have an X polarized in, we can generate Y polarized scatter field. And for this one, if we look at the scatter field of cross polarized, even though it is a single layer, but we can cover the full 360 degrees circle. Of course, the price we paid here is the magnitude. We have a maximum value of 0.5. So that different way we can break the limit. And through this example, so we would like to emphasize, beside the full wave simulations, there are some theory behind that need to be investigated. And now, the next just show some of the examples, some devices and systems. Of course, the first one that we have been working on many years is about reflectarray and transmitarray. The one on the left is an example of the Ku band reflectarray. So by varying the size of the patch, so we can have a focused beam. So if you look at the surface, it's really like a holographic surface. And with this design operating at 12.5 gigahertz, 3-meter aperture, more than 76,000 elements, so we get a gain about 48.9 dBi. So that's one reflect design. Another example is a transmitter design, transmitarray design. So in this design, we have the feed on one side and the beam on the other side. So we use this dual layer design with vertical vias. So this antenna work at 20 gigahertz with a 33 dBi gain and 5.9% bandwidth. So in these two designs, the beams are fixed. And in many designs, we would like to have a scanning beam. So if you look at the scanning beam, the key point is to have the phase of each element to be tuned. So nowadays, we see the traditional way or the major role is to use this phase shifter or the TR module or the TR chips to change the phase of each element. So I would like to call this is a downward, the frequency move down. And then we use the circuit approach to do this modulation. And now if we have this kind of the progress of the surface, so we can move the phase modulation upward. So use this reconfigurable surface. So each element with some reconfigurable pin diode, rect diode, so we can use the so-called field approach to generate a high gain scanning beam. So it will have the advantage in terms of cost, power consumptions, and weight. So here we show some prototype design. So this is one design, covering the conventional slot array with two phase shifting surfaces. So they have different gradient. By rotating these two surfaces, one from here, so this is a rotating axis, and this is another rotating, and then the surface will rotate in the planar. We can scan both elevation and azimuth angle. So that's the rotation. And if we break down this rotation into each element, so if each element here can be rotated by a micromotor, so we can scan the beam, we can also shape the beam. So that's another design. So furthermore, if we want to increase the speed, so we change from micromotor to the pin diode. So this is another prototype shows a 1600 element dual frequency electronic beam scanning. And this is just a video showing how this 1600 element work. So this is a patch. This is where the pin line locate. This is a biasing line. And then if we control them with an FPGA board individually, and we can scan the beam. So this is the phase distribution. This is what we really realize. And this shows the measured beam, how it will scan in the space. So that is a demo of the electronic beam scanning. So beside the antenna, we can also use the surface for the spatial power combining. So this is a power combining for the millimeter wave using the waveguide structures. So we have 16 channel input and 1 channel output. It is limited by size of the waveguide. And also by Dr. Rosenberg, this is early in 2003, he talked about the grid amplifier. So which can enable high power millimeter wave system. So that means we have the grid, and on each grid point, we will have amplifier, and they are assembled in space. And similarly, we also, following this work, we design a reflectarray with the power combining feature. So that means each element here, so we will have a small amplifier, and then the wave come in, amplified, and goes out. So with that, we can do the spatial power combining. So now we have the antenna, we have the circuit, and then we can build the system. So of course, this is also early concept back to the 1995. People talk about this quasi-optical transceiver. So its architecture is similar to the traditional transceiver. The difference is now the circuit device has been replaced. The lump circuit device has been replaced by the surface devices. So we have the amplifier grid, we have the filter, we have a mixer grid, and we have oscillator grid. So basically, the circuit component is replaced by the field component. So there are a lot of things can happen right here. And furthermore, here we talk about quasi-optics. We can take the quasi out. We also go ahead to design some optical nano-surfaces. So this is one idea. We would like to do the beam split. So we have one beam coming, the light coming, and then we would like to split them to 2 different directions. So traditional optical devices, they use 3-dimensional lens to do this beam splitting. And here we would like to use just a single layer, a very, very thin planar beam splitter. So basically this is what we design. So we will have small disk with a diameter about 100 nanometer and large disk about 200 nanometer. So they will have 180-degree phase difference for reflection. So by arranging them in this kind of pattern, we can realize the beam split. So this experiment, although the fabrication is really difficult, but the experiment is quite relatively easy. So we have a laser generator and we go through several mirrors, and then the light coming from here to our sample. This is where we put the sample. So the light come in and then split it into 2 different directions. So we turn off the light, so we can see the light coming here and split it into 2 beams. So that's first one example. We deal with the nano-surface. So we move the reflectarray concept from microwave to the optics. And then another example. So if we can split the beam, we can also focus in the beam. So this just shows a planar focusing lens. So we designed the surface with 400 micrometers in diameter. And then this is a small cell. So we see by rotating this element, so we can focus the beam. So in this one, a very interesting is about the FOOD ratio. The diameter is about 400 micrometer. And the focusing point is 100 micrometer. So this cannot be realized using the conventional lens. But with this kind of a surface, we can realize very close focusing. So if that be possible, so we go back, we see what can we use for these features, a very small focus. So this just shows I think this is a camera in a cell phone. So if you look at this one, these two camera is in the vertical dimension, but this one, because it's lead a long axis, it has to bend the light from vertical to horizontal. This is just because if you look at the lens, their focus and their dimension must satisfy based on the refraction index of the glass. So with the conventional glass, we always have the F larger than the D. But if you use the metal lens, we have not this restriction. We have no restriction on F over D. So with that, we can design a monolistic integrated telescope. So that means if we have glass right here, on the incoming surface, we put a metasurface. On output surface, we generate another metasurface. So not just using a single glass, so we can realize a telescope. So basically this is what we have. We design one objective, one eye lens, and then this is a comparison. So the top one is the conventional telescope. They have to use multiple lenses, objective, eyepiece, and usually their distance is dozens of millimeters. But now we can use just one piece, for example, 1 millimeter glass, we coat it with two surfaces. And then we can also realize the telescope function. So it is a single chip, ultra thin, and very easy to integrate. So we design and fabricate one sample, and we set up a measurement system. So this is the original target, and then this is a sample that we design and we put it right here. So we see the experiment. So this just shows, this is original image. And then we insert the telescope we designed, the glass with two metasurfaces on object on opposite side. So we see we really get another small fold right here. So with that one, we can get an inverted smaller image of 4. And still we have a large image 4 right here. This is because of the no polarization efficiency, which will be solved in the next step. And then we also measure the length of the original letter 4 and the new letter 4. So we see their ratio again as with a ratio of 4. That is actually what we designed to have. So that's a single chip telescope. So we move from microwave to optics. So now to summarize, I think I've been talking a lot about prospectors. So in my personal opinion, this surface electromagnetic is an area still under constructions. A lot of things has happening. There are many more to be discovered. And about the framework. So according to what we discovered right now, from uniform, periodic, quasi-periodic, and time-space modulation. So these devices are still, we call it linear device. So if we look at this circuit area, we look at how the circuit is developed. A very important step is to have the non-linear component, like something like a pin diode or transistor. So if we can design the surface with the non-linear functionalities, I think that will be a very important step. We need to design some non-linear surfaces. And then these are on the device level. So if you look at the bottom, the fundamental level, like in the circuit, we have the KCL, the KVL laws. In transmission line theory, we have the telegraph equations. We have the characteristic impedance of transmission line. So for the surface, so what will be the eigenparameter of the surface? And what will be the efficient equation to handle the surface relation? I think these still need to be developed. And we already see some progress like the GSTC in here. And I still think there's a lot of work to be done here because of the vector features of the field. So we have the basic, we have the devices, and more important is the system level applications. In the communications, in the radar, in the imaging, and also the computing. So I've read some works, they use the surface to design the neural network at optics. So that can be also very interesting. So this is a lot of things to be discovered in the surface electromagnetics. And just to name a few research topics, the fundamental theorems. So the eigenparameters of the surface, just like the characteristic impedance and propagation constant of a transmission line. With those two, we can describe a transmission line. And what eigenparameter we need to use to describe a surface. And together with these eigenparameters, the analytical approach and numerical method, and also the interactions of electromagnetic wave with the surface. And next, the surface design. The surface design at microwave, terahertz, and optical, the control of the magnitude, phase, and polarization, and also the anisotropic real-time control, nonlinear surface, a lot of things to be investigated. One interesting way is to see what we have already in the circuit. That we can repeat that with a field design, like filter, phase shifter, we already have those surface design. The diode, the transistor, can we have some surface design with these functionalities? And finally, the engineering applications from the device to the system, the antennas, the metal lens, communications, radars, and computing. So here just show some example that we have worked recently. One is to have a spaceborne or airborne station. So we place this kind of very low cost and no power consumption, lightweight phase array on top of a drone. And when it goes up, it will have a longer coverage. And also because if we move up, the high power, the focus beam will also change according to the rotation of the drone. So we need to automatically compensate the rotation of the drone so that it can keep focusing on our original user. So this just shows one example. So we see as far as it move up, so we will have continuous connection, continuous image. So it goes up and it keeps on rotating. So we can have a stable connection. If we go a little bit fast, let's see. So finally, we have this one goes up to 13 meters. So we have a very nice stable communication. So this is one example. Another example we have done is for the millimeter wave station for the 5G communication to reduce the cost of the massive MIMO antenna. So we use this kind of surface and then with a feed. And let's see. Sorry. So this is a high definition imaging that we are transmitting. And this mimic a communication system. And this is an antenna. And this is a feed. So by change the on and off of each element, we can do the beam shaping, beam scanning, multiple beam. So we can do the 1-to-1 transmission, we can do the 1-to-2 transmission, or we can scan the transmission from one to another, together still with a high transmission data rate of near 3 gigabytes. So this is a millimeter wave station. So to summarize, so we are focusing on these two-dimensional electromagnetic phenomena and properties. And then we think it is a lot, there are a lot of great challenges, but of course, it's also a grand opportunities for our researchers. So a lot of new things to be discovered. So just at the end, I would like to introduce this book, which was published in June of 2019. So we have a lot of collaborators to put this attitude together on the surface electromagnetic. We talk about the theorem, the surfaces, and applications. So also I would like to take these opportunities to thank my colleague, my students. So without their help, so all what I showed just now will be impossible. Thank you very much for your attention.
Thank you very much, Professor Yang. That was very, very interesting. I'm just going to stop recording here so I can open the floor to questions.